We're going to be taking a look at 2.6 special functions. Our objective is to identify constant, identity, absolute value, greatest integer, and piecewise functions in two manners. One, by the equation, by looking at the equation, be able to identify which one we're talking about, or by the graph. And so those are the two things we're going to be taking a look at in 2.6. Let's just do an overview of the different functions that we're going to be looking at here, the 5 different functions. The first one is a constant function. The constant function is a linear function in the form y equals c. So an example would be like y equals 4. Okay, and we'll talk about that one first when we get to them, but that's a horizontal line if you're talking about the graph of them. The second one's going to be identity function. It's also a linear function, but it's in the form y equals x. And again, that one's going to be a slope of 1 that goes through the origin, but it's still a line. The third one is an absolute value. We're comfortable with this. It's a function of the form y equals the absolute value of x. So definitely if you see an absolute value symbol, you're probably going to be doing an absolute value function here. The graph of an absolute value function is going to be either a v or an upside down v. The next one's going to be the greatest integer. The next two actually are going to be the ones that are going to be new for us probably. Greatest integer function. Another name for that is a step function. And we'll put that in your notes when we get to the greatest integer function when we talk about it more specifically. But it goes in this form y equals. Now these are not the same as absolute value. So I'm going to write it again to make sure. But what it is they're brackets. Okay. So whenever we see brackets like that, and we're specifically talking about some type of function, we're talking about a greatest integer function, sometimes referred to as a step function. So we'll spend some time on that one, definitely a little bit more detail than the first three. The last one is a piecewise function. Piecewise function is simply one function, but made up of maybe 2, maybe 3, maybe 4 pieces of other functions. So it's little tiny functions inside of one big function. Each little function is restricted according to its domain out to the side. And so that's definitely one we'll spend some time. We'll probably only graph this one. We'll spend some time looking at greatest integer. We'll skim through these first three. You just need to memorize what the equations look like and then also what the graph of them look like. So let's first start with the constant function. And the constant function is y equals c. C represents a constant. That's what we're talking about here. So some examples would be like y equals 3. That's what we have graphed right here. Notice it's a horizontal line at 3. We could have y equals -2, or y equals 0, or y equals 1/2. But notice y is by itself. When y is by itself, we're talking about a horizontal line. Okay? Horizon is one student in the past has said to me, and I thought that was pretty good, to remember that a horizontal line is when y is by itself. And so what we have are some examples over here to the right, and what you have is just simply moving the horizontal line to -2 to 0 or to 1/2. Okay? Now when x is by itself, that's not a function because it's a vertical line, so that's why we don't address it at all in this section because we're talking about special functions. The next one's the identity function, and when we're talking about the identity function, what we're talking about here is a linear function of the form y equals x. Now it has to be in that form. It can't be y equals 2x. It can't be y equals -x. It has to be y equals x. And if you remember back in chapter 1, we talked identity property with start equals the end. So if this is 2, then the end is 2. This side equals that side. That's the identity. It doesn't change. Okay? And so what we have here is that when x equals 1, y equals 1. X equals 2, y equals 2, and so on. X equals 0, y equals 0. And it creates this line. So here's some must-haves for it to be an identity function. The first one, it must go through the origin. It must go through the origin, otherwise it's not an identity. The other one, it has to have a slope of 1. If it has a slope other than 1, -1, 2, 1/2, whatever, not an identity. If this graph has been shifted up or down or to the left or right, it is not an identity function because it must go through the origin with a slope of 1. So far we have a constant function which is horizontal, identity function which goes through the origin with a slope of 1. The next one is the absolute value function. Again, the dead giveaway is going to be the absolute value symbols. So when you see an equation with absolute value symbols, hey, it's an absolute value function. Now graphically, how we can determine that is exactly how we do it in class. So when I ask you what should come to your mind when you see an absolute value, you want to think 2 cases. However, when we say 2 cases, that helps us solve equations. But graphically, when you hold up your fingers, don't you make a V? Now, it could be also an upside down V, but whenever we are graphing absolute values, we want to think of a V. We want to think 2 cases, our fingers make a V, and there you go. So far we have a constant which is horizontal, identity goes through the origin with a slope of 1, and absolute value which are v. Those are the most common. The next two we're going to spend a little bit of time on. The first one is called the greatest integer function. Another name for this is a step function. Now the reason obviously they call it a step function is if you look at the graph, it looks like stair steps. Now it could be going up like this, it could be going down, these lines could be a little bit longer, there could be more space in between them. All that is dependent on what type of problem we're dealing with. Now what it means to be a greatest integer function is this. It means that we're the results of the y, which is the result of the greatest integer of x, so whatever we plug in, the result of that has to be an integer. So in other words, x can be anything. Notice the domain's all reals. It goes to the left and right forever. And it goes up and down forever, but notice there's a gap between 1 and 0, and between 1 and 2. So notice no y values exist in between the integers 0, 1, 2, 3, and 4. All my y values fall on perfect integers. That's why they call it the greatest integer functions, that all your y's are going to be integers. Let's look at some and evaluate some of these here. So let me put up some examples for you. Okay, so let's put up 2 and see what we get with that one. Then we'll do a few more. How about 2.1? And we'll do 2.3. Then we'll jump to some larger ones here. Let's do 2.7. And 2.9 and then 3. Okay, so let's go ahead and evaluate this. Now, I've mentioned this as I call this the Price is Right rule. Okay, the Price is Right. Now, if you remember Price is Right, the game show, you're trying to guess the closest value without going over, and that's the key, is we can't go over. So what we're looking for here is the closest integer without going over. So on a number line, when we're talking integers, we're talking about the numbers we typically put on a number line. 0, 1, 2, maybe even -1, 3. I'm going to actually separate 2 and 3 a little bit since that's what we're using here. But those are all called integers. So I want to know what's the closest integer without going to the right. To the right means getting larger or getting bigger. So we always are going to the left. So that's something you may want to note. Graphically, you're always dropping to the left. I don't want to call it rounding. I don't want to call it truncating necessarily. Just remember you're always going to the left. And so we can get some negatives, because we're going to do some negatives here in just a moment. Let's do like negative 2.2. We'll just do a few for time's sake. And negative 2.8. Okay, so we'll do those and see what we get there. So we'll do those in just a moment, but let's go over here and do these. So the 2, let's go ahead and plot 2. So I'm going to do that in black. And so I put 2 right there. So what is the closest integer to 2 without going over? Well, 2 is right on top of 2, so that's the closest integer without going over. How about 2.1? Now 2.1 is right here. Okay. And I want to know what the closest integer is without going to the right. Well, if I go to the right, I go to 3. I can't go that way. I got to go back to the left. What's the closest integer? Well, 2 is. So notice when I do 2.3, I'm going to do the same thing. I would be dropping back to 2. 2.7, now this is where things start becoming a little bit different. Here's 2.7. 2.7 is closer to 3, but remember, Price is Right rule. We can't go over 2.7. I can't go to the right. I got to drop all the way back to the left. And so it goes back to 2. So a lot of students think we must be truncating, which is somewhat true until we get to the negatives, and then we'll take a look at that point. But at 2.9, okay, really close to 3, again, we got to go back all the way to 2. The only time we don't drop back to 2 is when we get to 3, because then it jumps up to 3. So graphically, 1, 2, here's 3, 1, 2, and there's 3. If I plot my points, notice what I have is when I get to 3, it's going to be open. So it's going to stay 2 the entire time between 2 and 3. Then it jumps up to 3. Then it's going to stay 3. And there's going to be your stair step. So you sort of get in the groove of how to graph these. For us, we're trying to, just right now, just identify the graphs and at least be comfortable with what a greatest integer or step function looks like. Now let's look at the negatives real quick. So I'll get rid of some of this stuff here, and we'll do this really quickly. If you take a look at these negatives, and let's call this 0, and we'll call this -1, -2, -3, and -4. If we go up here and evaluate this, -2.2 is right here. I can't go to the right. So what's the closest integer without going over? -3. I always go to the left. -2.8, well, that's closer to -3. and so it's still negative 3, and then negative 3 is also negative 3. And so what you end up getting is at negative 3, and then until you get to negative 2, and once you get to negative 2, you jump up and you get those stair steps again. So be very careful with negatives if you ever encounter those. Sometimes those are a little tricky. Okay. The last one we're going to take a look at here is what we call a piecewise function. This is the one that we're going to spend some time graphing on. What we have is a function, and it's made up of pieces of other little functions. So in this case, what we have is we have some type of f of x or g of x. And then what's equal to is a piecewise. So here's an example. Let me just give you an example. 2x plus 1 and x minus 3. Each of these have a condition. Each of these conditions have an end and a start point. So it'll look something like this maybe. Something like that. And so what we have is two little functions that make up a larger function. Each of the functions are tied to sort of some restrictions. Where the function is. And so what we get graphically is this, it's sort of looks like a weird graph because it's, like this one just goes and turns the corner. This one jumps. But notice they still pass the vertical line test. If I throw up here a vertical line real quick and move it around, see it only touches 1 point, and right at the corner still touches just 1 point. Over here, 1 point, 1 point, and even right there, it only touches it doesn't touch any point because it's open and open. Okay? And so maybe one of these are closed in. That's still okay. It only touches 1 point. I can grab the line. There we go. It only touches 1 point still. Now, the only time it wouldn't be a function is if I did something like that. Now, all of a sudden, it touches more than 1 point. If you notice, it touches 2. So we're never going to have that if we're talking about a piecewise function. Okay? So the graph of a piecewise is going to be a bunch of little functions made up there. It's going to be a weird-looking graph. So we've got greatest integer graphs, which are steps. Okay, that's what we just did over here. We've got absolute values, which are v's. We've got identities, which go through the origin with slope of 1. And we've got a constant, which is horizontal. So first off, the graphs of these you need to memorize. And then the different equations, you need to be able to recognize, oh, when I see this, what we're talking about is a piecewise. The last thing we want to take a look at is actually how to graph piecewise functions. And so let's take a look at this. Now, what I'm going to do to help you out is I'm going to put up sort of a shield here. So that we can make out what we're doing. Now, I'm going to label these, okay, each piece. The first piece is I'm going to label as a 1. Okay, so that's the domain that's tied to that one. And I'm going to come over here and I'm going to use a T-chart to represent that. Now, this value over here is called the end start point. Or what I call the end start point. And that is very important because that's where all the action occurs. Over here, this is an end point, and this is a start point, but it also has an end point, and then this has a start point. And so when we get down to this one, we actually have a few different ones. But up here, what we have is we have an end point for that one, because we're ending at 0, and this one we're starting at 0, so we have a start point. So all the actions occurring at the end and start points. So on the first one, all we have is an end point, and it's at 0. So I'm going to come up here, put end point 0, and notice that I'm going to include the end point, so it's going to be colored in. Now, how do I evaluate the y? Simply plug it in up here, and you get -2. So 0, -2, and it's going to be solid for this one, is going to be my end point. Now, what other values am I going to plug in? Well, notice I've blocked everything to the right because all my values are left. Now, I know this is y and we're using the x, so just you can change that to an x if you want. But what we have here is everything left of 0. And so what we have is we have like -1 and -2, -3, and so on. Well, if I plug those in, I get some more ordered pairs. And now I can go and say, look, I have a line that ends at 0, -2. Now my second one, we'll label right here, T-chart number 2. I have a start point, which is at 0. It's going to be open at 0, so I'm open. When I plug in, I get 3, so 0, 3 is my start point. So in this one, notice that all my domain is everything greater than 0, so I'm going to block everything left of 0. So if I go up here and I plot 0, 3, let's move that just a little bit more here so I can see, there we go. And so 0, 3, it's going to be open right there. That's my start point. Well, how far do I need to go? Well, it's everything greater than 0. So 1, 2, 3, 4, and on to infinity. If I plug those in, I get 4, and I get 5. Now, where am I plugging them in at? Right there. So 1, 4, 2, 5, and there's your second piece of the function. Now, if I get rid of that right there, Now you can see the piecewise function passes the vertical line test, and I'm able to graph. On this bottom one, we do the same thing. I'm going to do this one fairly quickly, so if you just stay with me here, and you can rewind if you need to. Hey, what we have is this is going to be my first one. Do it in blue. Okay, I have an endpoint at -1. It's going to be open. I plug in -1, I get -2, and it's everything left of -1, so that's like -2. So I get -3, or -3, I get -4. So -1, -2, -1, -2. It's going to be open. That's my endpoint. And then I plot the other points, and there's my first piece of the function. The next one I'll put in red. I'll put number 2. Now notice this one's a little different. I have a start and end point. So I got -1's my start point. I got 1's my end point. What's in between them? How about 0? So I got start point, I got end point, and they're both going to be closed. And so I plug in -1 right here. 2 times -1 is -2 plus 3. So I got -2 plus 3 is 1. If I plug in 0, I get 3. If I plug in 1, I get 5. Okay. Now that we've found some points, let's go ahead and plot these points here. And so what we have is we have our start points at -1, 1, and it's going to be closed. And then what we have is we have 0, 3, and then we have 1, 5. So I need to move this over a little bit and graph the 1, 5. And so we got our start, our end, we connect the dots, and there we go. And so there's your middle part. The last one I'll go ahead and do in purple. What we have on this one is we have just a start point, which is 1, because everything's to the right of that. It's going to be open. So if I plug in 1, I get -1, and it's everything to the right of 1, so 2 and 3 and so on. And so I get these values. And so now it's really just time to plot all those points. And so we go to 1, -1, and it's going to be open. That's my start point. And then 2, 0, 3, 1. You can see that line. And whoop, there you go. I'll get rid of that so you can see it. And there's your piecewise. It looks really nasty, but it passes the vertical line test. And it's made up of 3 little pieces of a function. Now at the very bottom there's a quiz here. We may do this in class, but if you have time to plug that in and give this some practice on identifying the different functions that we just took a look at. And a real quick review, what we have here is we have a piecewise function, which are made up of just pieces of functions. What we have in the net right before is greatest integer or step function using the brackets. We have absolute values, which are v's with the absolute value signs. Identity function goes through the origin with a slope of 1. Y equals x, and then the last one is a constant function, which is horizontal, y equals c. Well, those are the 5 different functions that we'll take a look at in 2.6 with these special functions. We'll see you next time.